So for this presentation, I'll be discussing my experiences and findings from our paper, which draws upon work done in connection with my master's thesis. The thesis demonstrates possibilities and pitfalls in the intersection between humanities data and computational methods, specifically using supervised learning techniques. So we collaborated with domain experts, David and Estelle from the Paris Bible Project, which some of you may know. And as part of their ongoing research, they were curious about the applicability of machine learning for the detection of biblical figures and their hand gestures. So the name Paris Bible essentially refers to a format or a style of Bible that was standardized around the 13th century, where thousands of Bibles were created and distributed around Europe. And a share have been digitized and annotated by different private and public institutions, which make them among the most important kinds of manuscripts for scaled and computational research and understanding religious mindsets and practices in medieval Europe. So a bit about the data. Domain experts gave us access to a subset of the Initiale data set, which contains around 11,000 scans of physical Bible pages. Around 5,000 of these have been annotated, resulting in over 1,700 unique labels. Label frequencies for each class range from merely 1 to over 3,000. And each image has between 1 to 67 annotations. So the illustrations represent biblical scenes, and they contain a rich tapestry of persons, objects, and symbols and actions. And needless to say, an image corpus like this requires substantial time and effort to annotate, which is why the data is only partially annotated at the time. So to construct a data frame for our purpose, domain expert helped us assemble a list of names and hand gestures, which we were happy about since the data was in French. And of the 5,000 annotated images, around 1,700 contained a name distributed among 32 classes, and around 1,600 contained hand gesture annotations. So while there are often multiple people represented in an image, the metadata usually only has one name assigned to it. And when it comes to the hand gestures, each image is annotated from everywhere from between 1 to 7 annotations. And there's a specifically interesting class here, which is the covered hand, where we have to classify a hand that cannot be seen. So looking at the class distributions visually, we see that apart from the large label space, there are noticeable variations in class frequencies, which quickly becomes a problem, dividing data into train, test, and validation sets. The learnability of less frequent classes becomes a concern as well, as they may not receive sufficient representation in the subsets. So what we decided to do was, I'll just go back, sorry. As you can see here in the persons plot, the names can be separated into 3 categories of saints, prophets, and kings. And because of the big label space, we decided to create a third data set called titles, where we used these three classes. We decided to take advantage of the fact that that the classes could be merged. So we essentially ended up with 3 different tasks, 2 multi-class classification tasks of biblical figures, multi-class classification of saint, prophets, and kings, and multi-label classification of 5 hand gestures. And I forgot to say that we had to make a decision of cutting out all data instances with frequencies below 100 because they simply couldn't, we simply couldn't represent them in all subsets. And even though that's not the best solution for things, that was what we could do with the time we had. So just to clarify, multi-class versus multi-label classification. For multi-class classification, each input is assigned to one and only one class. And for multi-label classification, each input can be assigned to multiple classes simultaneously. So to address the problem of class imbalance, we tested common techniques, including training with weighted classes and oversampling. When using class weights, we modify our training algorithm by assigning each class an individual weight based on its frequency. So the classes with most instances get the lowest weight, and so on. And this leads to classes getting equal importance during model training. And since we're operating in an algorithmic level, the technique can be used both in the multi-class scenario and in the multi-label setting. However, when we use oversampling, for instance through data augmentation, we create synthetic examples of images that already exist in our image corpus. And doing so in a multi-label setting, we can't help but oversample the entire label set. So when we oversample a minority class, all other classes are oversampled as well, even if they are majority classes. And it was surprising to us to see how few options we have for dealing with imbalanced multi-label data frames. So for each problem, we trained a number of different models, some without applying a balancing technique, and others with either class weights or some type of oversampling. We used convolutional neural networks with efficient net architecture pre-trained on ImageNet data, and we performed a grid search to determine model capacity and parametric values. So applying this model to the classification of biblical figures gives us a performance in the range of 50 to 53% accuracy. And while differences are marginal, the model trained using weighted classes performed best. And we noticed that, that class-wise performance was pretty good for a minority class, St. Jerome. We decided to manually inspect this class, and we saw that in many examples, St. Jerome is illustrated in the same fashion, wearing a red hat, which shows how in-class similarity and inter-class distance can affect learnability. As we expected, limiting the annotation space and constructing more populous groups for saints, prophets, and kings led to better performance. It led to an accuracy score in the range of 61 to 66%, and we see that models suffer when it comes to predicting minority classes. Our best performing model for classifying hand gestures is our original model without regards for varying class frequencies, which had a Hamming score of 60%, which is basically the multi-label accuracy, so to say. And similar to all previous models, we see performance is low for minority classes. So even though our initial results are modest, we believe that we can improve performance by taking advantage of our large pool of unlabeled data. And this is something that, for instance, can be done through active learning, which is a learning paradigm that puts the domain experts in the loop. It involves an iterative process where the algorithm selects instances from the unlabeled data and asks human experts to provide labels. It structures and guides the labeling process by focusing on the most informative or uncertain instances, making it more efficient and comprehensive than randomly labeling data. But on the other hand, the accuracy and reliability of the active learning process depends heavily on the quality and consistency of the annotations that are provided by human experts, which is the case in all labeling scenarios. Active learning algorithms also require an initial set of labeled examples to kickstart the process, which still involves a significant labeling effort. And while it can be a solution for our problem with limited data, we likely still have we'll likely still have problems with minority classes. We also believe it will be valuable to analyze our model's decision-making by, for instance, visualizing activation layers. This way we can see if our model includes components outside our area of interest when classifying an image. So, for instance, layout components like the frame or the angle from which the image has been scanned. Some of them are full page scans, while others are close-up of the illustrations themselves. And if this differs from one class to another, and finally, if it's necessary to limit the search space for our model by adding bounding boxes, which it probably is in our case. So finally, we believe that explaining our process along with challenges demonstrate the non-trivial nature of the intersection between humanities data and computational methods. And it can serve as a demonstration of the applied machine learning process and its requirements for domain experts within humanities who are considering machine learning in their work. We believe that clarifying and demonstrating pitfalls of the applied machine learning process, when dealing with unstructured and limited data, can help others make better decisions for their projects and so on. Thank you.